Y13 Ampere's law. Biot-Savart law determines the magnetic field. In general, it is a magnetic field is generated by the current density. However, this one can always be simplified into from this volume integral to a line integral that along a curve, and the circuit current, because charge is conserved, unless some charge is accumulated at some point. For example, the parallel plate capacitor, if you current flows in and there is a capacitor and charge is accumulated and the current does not flow. However, we assume that circuit is closed and the charges are flowing along a closed path. And we want to compute the magnetic field by making use of Biot-Savart law using this path along the integral along a closed path. This closed path means the circuit. The magnetic field is generated from the current element, and this is the basic structure of the magnetic field. First of all, we have a field point P that is, we have origin somewhere. This is expressed as x vector. And the current is the source, so we locate different notation, that is x prime. And from the source to the field point, there is a difference, displacement from x prime to x. And because the expression is too busy, we have introduced capital R that represent x minus x prime. And this is not just a simple times, this is a cross product. So using this expression, we can always compute the magnetic field as long as we know the explicit geometry of the circuit. By the way, we are very familiar with this x minus x prime divided by its magnitude q. That appear in Coulomb's law. So magnetic field also satisfies the inverse scale law. However, as you can see from this, magnetic field is a little bit complicated. It's around, if there is a current, magnetic field is circulating around the current. And the magnetic force is different from the electrostatic force or gravitational force that are central because of this kind of cross product. Let's return to a simple, straightforward calculation. Previously, we considered 1 over r, and when we use r, it was x squared plus y squared plus z squared. Actually, this is nothing but the difference from origin. However, because we have distribution of current over space, so we want to introduce the reference point by shifting from the origin to a point where the current source is placed. However, the partial derivative with respect to the coordinates of the field point is independent of the this is y minus y prime and z minus z prime. Y minus y prime, z minus z prime. Wait a second. Okay. Anyway, minus 1 over r, it's minus a gradient. We remember this one. This one is r x vector divided by x vector cube. So this one can be used to find the result. What we have done is just a translation from the origin to the x prime. Okay, so we make use of this identity. Calculation of magnetic field along a path, a circuit carrying current I. This one is to be replaced with minus gradient 1 over r. And this one is by definition absolute value of x minus x prime. And just to remember the final result, if there is a scalar field and constant vector, its curl is nothing but the gradient of this scalar field cross product with this constant vector. Memorize this result. And because of that, we have a cross product with gradient, and that can always cross product with gradient that can always expressed as using this formula, substituting phi, this is a 1 over r, and this is a c, and this vector is phi of x. Therefore, this one can always be expressed as a curl of something. And this A is called the magnetic vector potential. We remember it is a very similar to the x minus x prime dq 1 over 4 pi epsilon 0. You remember this. This is electrostatic potential. Electrostatic potential. It is very similar in shape. However, electrostatic potential is scalar. However, this A is a vector. So we say it is a vector potential. And when we take the curl, then what we find is the magnetic field. That's the reason why we name this as the magnetic vector potential. Remember, both of them has a 1 over r style. And in here, numerator is a vector. This dx is along the path, the circuit. This path is identical to the circuit itself. Okay. Next, magnetic field is now from Biot-Savart law. Magnetic field is always expressed as a curl of magnetic vector potential. And magnetic vector potential is much easier to compute than the calculation of the magnetic field directly from the Biot-Savart law. This is the same as the case when we compute the electric field. We first evaluate the electrostatic potential and take the minus gradient to find the electric field. Because this scalar is much simpler to evaluate than the electric field using Coulomb's law. Anyway, divergence B is because the B field is the curl of A, and if we substitute this, we have divergence curl of magnetic vector potential. In fact, if we make this is a triple scalar product style. Instead, we don't have a vector, instead of vector operator. This the derivative operator can be included in a definition using determinant. And we know this derivative, these two gradient operators are identical to each other. When you compute the determinant, any two rows are parallel, then the determinant is 0. Therefore, it is trivial to find that divergence B is 0. I told you divergence of E equals rho over epsilon 0. However, magnetic field does not have any monopole and dipole. Sum of poles charges in the dipole in the magnetic field, it is 0. So we actually have found two among 4 differential form of Maxwell's equation already. And the other way to show the divergence B equals 0 is explicitly shown here by making use of the anti-symmetric nature under exchange of vector indices in the Levi-Civita, and the symmetry, this is a symmetry of the product of derivative operators. Let us make use of this definition of the magnetic vector potential to evaluate something. This is a circuit. The red one is a straight line where current is flowing, and the blue one is a circle. We have 1/2 L, 1/2 L, and there is the origin. We find a place where the field point is placed. We want to compute the magnetic field at this point by computing the magnetic vector potential first and take the derivative curl A to find the magnetic field B due to a current along a straight line. However, because a circuit must be closed, in most textbooks, they consider the red part only and they ignore this contribution, but it is important. It depends on the shape of the circuit, whether this blue part can be negligible or not. First, let me call this CL and CR. CL is the straight path and CR is a semicircle of radius r that is 1/2 of L. These are parameterization of x prime because we need to integrate over x prime that is along the circuit. So CL is a straight line, so Z varies from -1/2 L to +1/2 L. And CR is a semicircle, on the ZX plane. So cosine, sine, okay? In order to find the vector potential, we need to compute the absolute value, the distance between the field point and source point. So x minus x prime must be evaluated using this expression. And x is on the xy plane. We have chosen at the center. So we have x and y dependence only. There is no z component. This is the field point dependence, and this comes from the source point dependence. The differential dx prime can be evaluated from this. We know how to do that. This is trivial. Magnitude of the distance between the source and field, that can be obtained by taking the square root of this vector. And in here, it is a square root of x squared, y squared, z squared. And this one, square sum. The result is given in here. Now we substitute this one. First of all, we find the contribution of CL. The CL contribution integrated over -1/2 of L and +1/2 of L. This CL contribution is this. And we have substituted. We rescaled it with the Z. We have Z here, Z there. So Z rescaled with the rho, and rho cancels. It is divided by rho squared. So it becomes 1. So C is Z over rho. This integral, we are familiar with this integral. This integral, when we compute the electric field due to a charge distribution along a straight wire, we used this integral table, and actually we derived this integral table already. So we just substitute this. We find the AL contribution, because it is along a straight wire along the z-axis. This vector potential is parallel to E3. Next, we compute the contribution of this semicircle. This semicircle, if I make use of these parameterizations in here and substitute this one into the denominator, our result is like that. Before going ahead, we first take the limit as L goes to infinity. We would like to consider the infinite wire and infinite semicircle. If we increase the L to the infinity, this is proportional to L. Denominator is dominated by this one. They cancel. It becomes a constant field. If it is constant, what happens? If I want to compute the magnetic field, it must be obtained by taking the curl. And this is a derivative. If it is a constant, it is 0. Aha. So the contribution of this semicircle is absolutely 0. In the limit, L goes to infinity. So we don't have to worry about this semicircle contribution. So it is a vanishing. Anyway, this one is also proportional to E3. This contribution, although it is a finite, parallel to E3, anti-parallel or parallel, it depends on sign. And this contribution, straight wire contribution, it is also parallel to E3. In that case, it is a function of x and y only. Theta is a function of x and y. In here, we have x and y only. There is no z component. The z has been integrated out. Therefore, in the case of the straight wire contribution, the curve is simplified into two pieces. It is proportional to E3 only. So the final result for the curve is just composed of the two contributions only. So we can do the derivative. You can find out the derivative of this function, and the final result is like that. And in here, we can see it is a minus y(E1). This factor of 2 has been canceled to find a 2 pi. And we have a planar radius rho x squared plus y squared. So rho has been pulled out, and the numerator and denominator separated into minus y(E1) plus x(E2) rho. Okay, this one is actually minus sine phi E1 hat plus cosine phi E2 hat. You are familiar with this. This is E phi. Finally, what we have found is that along the straight wire, current I is flowing and magnetic field is turning around. It is a circle. It's just like the uniform circular motion, parameterization for the uniform circular motion. It looks like a velocity of a particle making a uniform circular motion. Current I flows, then magnetic field is making a circle. And the strength of the magnetic field is decaying 1 over rho. The reason why we do not have 1 over rho squared is because one dimension has been integrated out. So problem becomes a two-dimensional case, and inverse scale law integrated over a straight path along a single dimension becomes just 1 over rho style, two-dimensional problem. There is a mistake in here. It should be phi. Okay. The other term that is vanishing has been discussed in detail. Finally, straight wire generate the magnetic field along the direction encircling the current like that. Okay. Ampere's law is nothing but to reproduce this result, and more specifically, it is more general than the explicit calculation using Biot-Savart law. Okay. We evaluate this one. Curl B surface integral. And if we substitute this one in here, current density multiplied by mu 0, and current density multiplied by as a scalar product with the surface, what's that? This is current. Current I, we have a current density that varies depending on position. But when it passed the surface, integrated over surface, J dot this sigma over this surface, it is nothing but the current. So this is current. Enclosed means current passing through this surface only. Okay. Next one. Explicit evaluation of this current can be done by taking the scalar product of current density with the surface element, integrate over surface. This one can be done when we consider current distribution. We have a current distribution. This is a constant current density inside the cylinder. In that case, in total, I is flowing in uniformly. Then the current density can be written as I divided by the cross-sectional area pi r squared. If the radius is capital R, the amount of current can be evaluated depending on the cross-sectional area. For example, if we choose a circle of radius small r that is smaller than the capital R, what happens? Here, current I is flowing in, but here, because the area pi r square has I, this area, this is pi small r square. Therefore, the I enclosed by this surface or this boundary is just I multiplied by this pi r square divided by pi capital R square. If I substitute small r equals capital R, I can reproduce the total current I. So using this, I can find the magnetic field surrounding magnetic field at this small r radius by making use of Ampere's law, B dot dl or B dot dx along a closed path is mu I enclosed. And from here, we have B times 2 pi r small r and mu 0 times enclosed current small r squared capital R squared. Using this, here we used the rho. We find rho dependence in the numerator. Inside the radius of this big cylinder. Therefore, at the center, just like what we have done with the case in the shell theorem, field sphere, electric field due to a field sphere, So it is magnetic field due to current distribution filling a cylindrical wire. At the center, when we substitute rho equals 0, the magnetic field vanishes. But when we increase the radius so that it can enclose the whole amount of cylindrical current distribution, it is the same as what we have expected. Current I is flowing along a straight wire. Thin straight wire has a magnetic field 2 B0 I over 2 pi E phi. And its dependence is 1 over rho, the same. Okay,